Hello and welcome to a video lesson on one of my favorite topics in applications of trigonometry, which is polar graphs. In this first part of this topic, we'll be analyzing polar graphs and just getting familiar with some of the settings when we sketch them and really appreciating the beauty of what we're seeing in front of us. We'll sketch a polar curve that looks basically like what you see here, which is, kind of like a propeller. And sometimes when I sketch the graphs on my computer, I'll actually shade in some of the graph using the features of GeoGebra, which is the program that I use. And then I'll start to think about, well, what if I animated this? What would this look like? And so I think it's pretty neat looking. Towards the end of this video, I'd like to show you a few different polar curves, but really the next lesson is when we focus on all the unique curves that we can work with. So let me start with how we would actually find symmetry with polar curves. And obviously the first way that we can see symmetry on a graph or with a polar curve is to actually look at the graph and to see, is this symmetric around the x-axis, the y-axis, or what's going on here? So the only problem that when we work with the polar graphs, the polar equations, analytically working with symmetry, is that there's no x that we would plug in a negative x. So recall that if we were to calculate symmetry or find symmetry in a regular function, we would plug in negative x to see if the result ends with the same function that we started with or just the opposite function that we started with, as in a negative f of x. So what we'll do here instead is we'll be looking for x-axis symmetry, which is kind of weird because we're seeing the x-axis as the polar axis. We'll also be looking for y-axis symmetry as well as the origin symmetry. Now recall that, again, when we worked with functions and we're working with symmetry, there wasn't an x-axis symmetry because if a function had x-axis symmetry, it wouldn't actually be a function. It would just be a curve or a parametric equation. So we'll use this information on the next page when we actually do an example of this, but just for your reference, we'll be replacing r comma theta, so notice at the top here, we'll replace r comma theta with r comma negative theta inside the function, and we'll see what it becomes. For y-axis symmetry, we'll replace negative r and negative theta. We'll replace r comma theta with negative r, negative theta. And then for the origin, we will replace r with negative r, and theta will be the same. This one's the most intuitive to me because when we're actually sketching polar coordinates, and if we have r comma theta, say in the first quadrant or something, then if we work with negative r comma theta, we still have the same angle, but we'll just be going backwards along a straight line. So it'll be in quadrant 3, whatever point that we're plotting. All right, so these are the three tests, and these are the three things that we'll do to work those tests. So here's one example that will work, and I'll tell you a little bit about this curve. When we sketch this curve, we could sketch this curve in function mode, and we'll get just a regular sine curve that has a height of 2 and goes all the way down to negative 2. And its period is usually 2 pi, but divided by 2 ends up being pi. So it's a little bit quicker and it's in the period. Now the only thing we really care about with a polar curve is the actual 2 as a coefficient of sine. That's what's telling us how far this function is away from the x-axis. It's also telling us how far the function is away from the pole in polar mode. So the max of this function is 2, just like in function mode. All right, so to actually find out if this function, or I should just say polar curve, is symmetric about the y-axis, we'll replace r comma theta with negative r comma theta. So that's all I did right there. I just plugged in those values. Now, I could have maybe skipped a step and said that this is negative 2 theta, but I'm just going to write that over again and simplify it. So there I have that 2 negative theta simplified to negative 2 theta. And then the final thing that we will do here is think about the odd identity. The odd identity says that if we have a negative theta with sine being evaluated by sine, then that's equivalent to negative sine theta. So on the right side, what we'll adjust here is pull out that negative essentially. We're not actually factoring out the negative, but it looks like we are. And so that means that 2 sine of negative 2 theta is equal to negative 2 sine 2 theta. This actually makes a little bit of sense if you think about the triangles on a graph, like the bow tie and such. And now we'll just divide by a negative sign, and we'll get, sine as in SIGN. And then we'll get r equals sine 2 theta. So because the result is the same as what we started with, that proves that this polar curve has symmetry around the y-axis. Now I'll say this, kind of odd. If you can prove symmetry about an axis using algebra, then you've proved that symmetry. But if you look at a graph and you see that there is symmetry on there, it doesn't necessarily mean that it can actually be proven. I think I said that right. Just because you prove it, when you prove it algebraically, you've proved the actual symmetry, but there may be also another symmetry that didn't actually prove through. I haven't come across that too often, so don't quote me too intensely on that. Alright, so now if you have your calculator, you can go to polar mode, make sure it's in polar and radian mode, and go to y equals, and you can enter this equation in there. The theta symbol is just where x is usually. So 2 sine 2 theta, radian, polar, and I would hit like a zoom 6 at first, so a zoom standard, and then see what you get. It's likely that you'll get a small butterfly looking graph, and you can zoom in. So press zoom in, enter, and then enter again as your center point, and you'll get a bigger butterfly. So you'll notice that there's 2 types of symmetries. Actually, probably all 3. Alright, so with that said, I like, maybe you graphed it in, the settings were a little bit messed up and you didn't get exactly what you thought you should get. So here's just a mini lesson on some of the settings on your calculator so that we could get the best graph and the best viewing window. But like I said, the modes that we want to be in are polar and radian. So the first thing I want to say, I basically have 3 points here, and the first one is this. It's that, x, y, and theta should be adjusted in your window. Well, that's not the order they come, theta, x, and y, okay? And for theta, there's a theta min, there's this theta max, there's a theta step. I'm about to say something about the theta step. But then x and y have a min, a max, and a scale. I always keep the scale at 1, and x min and max, to have the ratio of 3 to 2, I'll talk about that in the next video, but a 3 to 2 ratio is good because that's the ratio in which your rectangular viewing screen is in. So, if the x's are negative 3 to 3, let the y's be negative 2 to 2, 6, 4, etc. Okay? So make some adjustments to those settings to get you a better graph. The other thing is to set the theta step to fractions of pi. So if you're in your window settings right now, you could just go down to theta step, and if you type in pi divided by 24, so that second caret button divided by 24, your calculator will immediately turn that into a decimal, which is 0.13 whatever. So if you ever see that, you know that you have a really good theta step. Now that's for a completely smooth curve. Now if you like an even smoother curve, then you just enter a smaller value. But be careful, it'll take longer to sketch. Now let's say you like a little bit of more of a geometrical look. So if you go to your window settings right now and you type in like, 0.5. So 0.5 will just make your shape look a little bit more geometric. Your theta is stepping larger. So you're not sketching as many points, so it looks more geometric, as in straight lines. Okay, so that's one thing. The next thing is just about the trace feature. And what you could do is you could just press trace and it'll automatically, I think usually, take you to the first theta value that you have set. So if your theta min is 0, then it'll just take you to theta equals 0. And then since your theta step is in a fraction of pi if you move right 24 times, you'll end up at pi, and it should say 3.14 on your calculator. And so if you're trying to figure out the range of one of these polar curves, the range is just the minimum and maximum R values. So you could use the trace feature and go all the way around and see what the minimum R value is, which interesting. If you press trace on your calculator, you will not actually see R values. Okay, so here's a way to fix that. If If you press second zoom, that's the format option on your T84. And I'm not sure if this works for some of the older T84s. I'm looking at a CE right now, and the very first option I have is rectangular GC or polar GC. And I hit enter on that, and I go back to graph and trace, and then I see R values. So if you go back to where you started with, I started with 0, 0, and I move to the right until I can see something like familiar values like that. So then you could see what the actual R values are. So if you get to if your curve actually touches the x-axis or y-axis, you can see what those values are on that axis. So for me, I'm looking at this very curve that we started with, and I have an R value of -4, and theta is 1.57, which is pi over 2. So that's the minimum R value. But then you could also move to another part of the curve, and you could see what the R value is. Okay, that's kind of nifty. I hadn't usually used that, so I hope that helps you. And then finally, the max R value is the max from the curve to the pole. I think that's also intuitive, but when we're talking about the max, we're not talking about a height or left and right. We're talking about how far the curve emanates from the pole, from the origin. So if you're standing at the origin where x meets y, how long does it take you to get to the actual end of one of the rose petals? You're not walking right then up or left then up. You're walking just straight towards that point. So I said the max R values from the pole to the point. Okay, well that's all I wanted to share with you. That's a little bit of algebra and a little bit of analyzing. And so I will leave you with a special curve for you to graph. And that is a super simple curve. It is R equals theta, which we will talk about in the next video lesson. If you put that in your equation, y equals, and change some of the window settings to go from -20 to +20 for x and y, then you'll see something pretty nifty. Thanks a bunch for learning with me.